Hello everyone, welcome to another tutorial on TURBOMOLE and its graphical user interface TMoleX. In this tutorial, I'll walk you through the process of calculating and plotting the UV vis absorption spectrum of the indigo dye molecule, which is a conjugated organic molecule historically used as a blue dye and often studied as a benchmark system for excited state methods. We will do this using two different approaches. One, linear response time-dependent density functional theory, also known as LR-TDDFT, using the ESCF module of TURBOMOLE, and real-time time-dependent density functional theory, or RT-TDDFT, using the Ripper module of TURBOMOLE. Before we begin, let me briefly highlight the key difference between these two approaches. In LR-TDDFT, we directly compute the excitation energies and oscillator strengths by solving a response equation around the ground state density. This method gives us discrete vertical excitation energies and is usually the method of choice for routine excited state calculations. In contrast, RT-TDDFT works by explicitly propagating the electron density in time under the influence of a small external electric field. From the time-dependent dipole moment, we then obtain the absorption spectrum through a Fourier transform. RT-TDDFT therefore gives the entire spectrum in one go rather than individual excited states. This tutorial is divided into three parts. In part 1, we will calculate and plot the UV vis spectrum using LR-TDDFT through TMoleX. In part 2, we will redo the same LR-TDDFT calculation manually using the terminal. We will use the Ripper module for the ground state DFT calculation, followed by ESCF for the excited state calculation. Finally, in part 3, we will calculate and plot the UV vis spectrum using RT-TDDFT through the Ripper module. One important thing to note is that since TURBOMOLE version 8.0, we do not always need to use the defined script to create a control file. Instead, we can create a minimal control file by specifying only essential information such as coordinates, basis sets, and the DFT functional. This control file can then be used to directly run DFT and TDDFT calculations. In this tutorial, we will use this minimal input approach, so it is important that you have the version 8.0. We will use the following basis sets for all calculations. The basis set will be def to SVP to keep things fast. For production level TDDFT or excited state calculations, a larger basis set such as def to TZVP, def to TZVPD are usually recommended. The exchange correlation functional will be CAMB3-LIP, which is a recommended choice for excited state calculations. The coordinates of the indigo molecule are taken from this paper. A direct link to the coordinate file is also provided in the video description. Okay, so let's begin with part 1. Here we perform the LR-TDDFT UV vis calculation using TMoleX. Start by creating a new project. Import the coordinate file for the indigo molecule. You can click on Open 3D Molecule Builder to visualize the structure and check that everything looks correct. Exit the Molecule Builder and click on Continue. Assign the def to SVP basis set and click Continue again. Then click on Generate MOs and move to the next step. The level of theory will be DFT with RI acceleration. From the drop-down menu, select the CAMB3-LIP functional. Leave the remaining options as they are. Set the auxiliary basis set to universal. For SCF convergence, we will use 10 to the power minus 7 for both the energy and the density. Click on Continue and now choose the job type. Go to Spectra and Excited States and select UV vis and CD parenthesis vertical excitations. We will calculate singlet excitations using the random phase approximation, which corresponds to standard LR-TDDFT. Set the unit to electron volts so that the excitation energies are printed in electron volts. Select Calculate all irreps and set the number of excited states per irrep to 13. Since indigo is treated in C1 symmetry, there is only one irreducible representation, so this corresponds to 13 excited states in total. Finally, click on Run and give the job a suitable name. The job first performs a ground state DFT calculation. Once the ground state density is converged, the LR-TDDFT calculation is carried out using the ESCF module. After the job finishes, we can inspect the output in the Results tab. At the top, we see the ground state total energy. The next section lists the excitation energies and oscillator strengths. The final section shows the circular dichroism results, including excitation energies and rotatory strengths. On the right, you can click on UV vis spectrum to visualize the absorption spectrum. The vertical lines correspond to the excitation energies and their heights reflect the oscillator strengths. The plot shows the excitation energy in EV on the x-axis and oscillator strength on the y-axis. You can also change the x-axis units to atomic units, inverse centimeters or nanometers. The spectrum is broadened using either Gaussian or Lorentzian broadening. The strength of the broadening is controlled by the standard deviation. Larger values lead to broader peaks. Now that we have seen how to calculate the UV vis spectrum using TMoleX, we will switch to the terminal and perform the same calculation using shell commands. I'll assume that you have TurboMole installed and can run basic commands such as ripper and ESCF. For this tutorial, we are using TurboMole version 8.0, which supports minimal input control files and also supports hybrid functionals in RT-TDDFT calculations. With the minimal input approach, we do not need to run define. First, go to the directory where you want to run the calculation. We start with the coord file, which I have already placed here. You can inspect it using cat coord. Next, we need the control file. I already have a minimal control file prepared, and let me briefly show its contents. Here we first define the atoms block where we specify the basis set and the auxiliary basis for RT-TDDFT. Next, we provide the name of the coord file containing the atomic positions. Then we specify the DFT functional and integration grid. After that, we define the SCF convergence criteria for energy and density. All of this information relates to the ground state DFT calculation. Next, we explicitly set the symmetry to C1. Finally, we include the keywords related to the LR-TDDFT calculation. The keyword SCF instab RPAS tells TurboMole to compute singlet excitations using the RPA formalism. The keyword SOES all 13 requests the first 13 excited states. Finally, we request the UV vis spectrum output in EV units. Now let's run the ground state DFT calculation using the ripper module. We type ripper, right arrow, output.ripper space %. This writes the output to the file output.ripper. The calculation finishes quite quickly. Next, we run the excited state LR-TDDFT calculation using the ESCF module. ESCF right arrow output.ESCF %. On my 32 core machine, this takes around 40 seconds. We can monitor the progress using tail -f space output.ESCF. Once the calculation finishes, we press Ctrl+C to exit the tail command. If we now type ls, we see that several new files have been generated. Among them is the spectrum file, which contains the data needed to plot the LR-TDDFT UV vis spectrum. To visualize this, we can use the Ripper Tools web application. Go to rippertools.turbomole.org. From the sidebar, select LR-TDDFT UV vis plotter, copy the contents of the spectrum file and paste them into the input box. Click anywhere outside the box and scroll down to see the spectrum visualized. Finally, we arrive at the third and final part of this tutorial, where we calculate the UV vis spectrum using RT-TDDFT with the Ripper module. Once again, we use a minimal input control file. All keywords related to the ground state DFT calculation remain the same as before. Next, we need to add keywords for the RT-TDDFT calculation. To generate these, we again use the Ripper Tools web application. Select RT-TDDFT input creator from the sidebar. Here we choose the electric field type and its parameters such as the amplitude. For UV vis absorption spectra, we use a weak Gaussian electric field and the default parameters are usually good enough. Copy this section and paste it into the control file. This part defines the external electric field. Next, we add the keywords related to the RT-TDDFT propagation itself. These include the time integration algorithm, total evolution time, time step, minimum and maximum energies for the spectrum, and the damping factor. The default settings are generally reasonable. However, for this tutorial, we increase the time step to 0.5 atomic units instead of default 0.1. For very strong electric fields or larger time steps or very diffuse basis sets, one may observe numerical instabilities or diverging energies. In such cases, it is advisable to use the ESCF based time integration scheme instead of the default predictor corrector method. Since we are using def2 SVP and a weak field, the default predictor corrector scheme works well here. More details about these keywords and their implementation can be found by scrolling further down on the Ripper Tools page. Now we copy and paste this input into the control file. At this point, our control file contains everything needed for both the ground state DFT calculation and the RT-TDDFT simulation. So we start the calculation using Ripper, right arrow, output.ripper, %. If we open the output file, we see that the ground state calculation finishes first, but the file continues because the RT-TDDFT propagation is now running. We can see the RT-TDDFT specific output in the file. If we type ls, we see several files with the prefix RT. The file RT energy contains the total energy at each time step and can be used to monitor stability. In our case, the energies remain stable. Next, we can inspect the RT dipole file, which contains the time-dependent dipole moments. Since we are using an evolution time of 1000 atomic units and a time step of 0.5 atomic units, we obtain 2000 time steps in these files. The UV vis absorption spectrum is written to the file RT-spec. This file is updated continuously during the simulation. If we plot it too early, the spectrum will not be converged. Therefore, we wait until the RT-TDDFT simulation finishes before analyzing this file. We can track the simulation progress using these output files. Type in tail-f RT energy to track the simulation progress. Once we complete 2000 time steps, we can press Ctrl+C to break out and see that the Ripper output file is now complete. It shows that this calculation took about 18 minutes, which is quite fast. Now we open the RT-spec file and copy its contents to plot the spectrum. We will now go back to Ripper Tools web app and head over to the option RT-TDDFT absorption spectrum plotter. Here we can paste the contents of the RT-spec file and see the absorption spectrum over a wide range. We can adjust the axis limits to the same ones that we use for the LR-TDDFT spectrum. And here is the final plot. We can now compare it with the plot we obtained for LR-TDDFT. Although the peak positions coincide exactly between LR-TDDFT and RT-TDDFT, there are still some small differences in relative intensities which can arise from the finite time window, damping, and field strength used in the real-time propagation. In contrast, LR-TDDFT reports the state-resolved oscillator strengths, while RT-TDDFT reflects the collective time domain dipole response under these numerical choices. So that's it. In this tutorial, I showed you how to calculate the UV vis absorption spectrum of the Indigo molecule using LR-TDDFT and RT-TDDFT with the help of TURBOMOLE and TMoleX. If you have any questions or doubts, you can leave them in the comment section down below. If you like this video, then don't forget to hit the like button and subscribe to the channel for more videos like these. Thanks for watching and have a great day.